which I'm talking about the performance of the production system as those green points. These are mentioned here. And what do you mean by the performance? It means that how the pressure is behaving, how much it is declining. For example, pressure inside the reservoir here probably is 2500 psi. Okay, then it is 2005. What? How much is the pressure here? Maybe 2000. Okay, how much is the pressure here? Maybe 1950. How much is the pressure here? Maybe 1500. Now you see there's a major loss, 1950 to 1500. The question as a production engineer, why? Why this is happening? And from here probably is 1100. Severe
So,
prediction. Yes.
how is the pressure difference, the performance of production, since the pressure difference is natural?
Pressure difference is one of them is natural and one of them is because of the restriction you are putting inside.
Uh-huh.
Okay. As you said, a very good point you raised. The pressure differential or pressure reduction could be natural or it could be man-made due to incorrect tubing or incorrect production system, or you can say plumbing system. For example, now you are using, at this point you are using a safety valve. You could use safety valve here 2.5 inch. You could, I'm talking about the ID, inside diameter of the pipe, 2.5 inch. You could use here, let's say 3.0 inch. Now, if you notice that this 2.5 is smaller, so smaller means there will be more restriction for the fluid to flow, and because of the restriction, there is a chance that pressure may be declined. Okay. Now, what is the exact size which safety valve you should put? 2.5, 3 inch, 4 inch, 5 inch, 6 inch. What exactly? This is your job to find out, so that the minimum pressure loss occurs. So how we relate this pressure loss with the size of the equipment? This is the biggest question right now. For example, now there's 1100 psi and the equipment is, let's say, safety valve. Now, which safety valve we should put so that this pressure loss should be the minimum? This is our job. This is what we are looking at, and this is what we will try to solve it. How we can select this safety valve in this lecture. It's this one, and next 3 lecture we'll continuously talking about this. Now, let's get back to the question that for your answer probably is clear now that there are restrictions, the pressure drop naturally, and there is a pressure drop because of the man-made issues. And we are here to solve the man-made issues, and I will talk about it in the coming slides. So now let's get back to the lecture. My point was that we are looking at the performance of the production system, which starts from the perforations towards the separator and so on. And when I say performance, I'm talking about the pressure reduction. Okay. Now, in the second step now, we have two terms that are important here. One of them is the inflow performance relationship. Other one is the vertical performance relationship. Okay. Now, inflow performance. What is inflow performance relationship? IPR. We call it an IPR. Probably you might have seen them in some of the research papers also. In especially the one today somebody was doing on underbalanced drilling and drilling engineering. They were talking about this IPR here. Okay. This IPR represents the performance of this production system, how this production system is behaving. We say that okay, it is because of the pressure, but how we put it in the graphs, how we really write it as a technical person. So we have a term we use it, which is the inflow performance relationship graph, or is a graph that we use in order to perform this production system. Then we have another term, we'll talk about both of them, the vertical performance one. This vertical performance relationship is talking about the reservoir performance. Okay, so I can write here vertical performance is related to reservoir And inflow performance is related to the plumbing system or production system. Now, since you know that in order to design the safety valve and the tubing string and all those production system, we need the performance of the well as well as performance of the reservoir, both of them. We will see that how we do that, and slowly you will know. But let's start as a basic concept. What is the inflow performance relationship? It it will make sense in this lecture. By the end of this lecture, it will make sense what I'm trying to talk. Now let's go further to the IPR. What is IPR? Inflow performance relationship. Inflow performance relationship is the measurement using the bottom hole pressure gauges at regular intervals as part of the field monitoring program. IPR is the relationship between flow rate and wellbore pressure. Okay, now let's look at it. What it does it mean exactly? Okay, let's say we have the well here. Again, we have a well. Now, you are producing this well at the surface. Here at the surface, let's say 200 barrels per day. Okay, which is, let's say, is 13 October 2020. You are producing now. When you are producing 200 barrels per day, what is the flowing pressure? What is the pressure at this point? What is the pressure here? Okay, let's say the pressure is 2000 psi. Okay, what I said before, we are looking at the performance of the production system. Okay, and when I say performance of the production system, we are talking about its pressures. How much is the pressure? How much it is reduced? Which equipment has reduced its pressure more, and so on. Okay, now let's do some more. We are producing now 400 barrels per day on 14th of August, 14 October 2020. Okay, on 13 October we are producing 200 barrels per day. On 14 August or 14th October we are producing 400 barrels per day. Now my question to you, will the pressure remain same or different? This is my question to all. Will the pressure will remain same or different? Well, pressure will be different. Okay, pressure will be different. Now, if you change the flow rate, it means that if you change the pressure, if you change the flow rate at surface, it will change flowing pressure inside the tubing. Okay, so flow rate has direct connection with the flowing pressure. Okay, higher the flow rate, less will be the pressure inside. So it has the direct connection. Flow rate has direct connection with the flowing pressure. Now, IPR is the term which is connecting both of them. This IPR is connecting both of them. Inflow performance relationship is the graph which is between the flow rate versus the pressure, and it tells us at this pressure, at this flow rate, what will be the pressure. Now let me show you some IPR.
Sir, did you say the surface flow rate and the tubing flow rate is directly proportional?
Correctly. You see here, now liquid flow rate is increasing and the pressure is declining. In this graph, you can see that. As I said, the inflow performance relationship is a graph between the well pressure versus the well flow rate. Okay, so here you can see it's a graph. Okay, this is the flow rate in x-axis, and y-axis is the flowing wellbore flowing pressure. Now, the question here is, what is the wellbore flowing pressure? Can anyone answer me? What is the wellbore flowing pressure? Anyone?
Is it the pressure on the pipes?
It is the pressure inside the well, in the tube, in the pipe. Okay, it is the pressure. It is the pressure which is inside here, inside the flowing pressure in the tubing. Not the one we are talking about in reservoir. The pressure inside the tubing string. Okay, so it is the flow rate, flowing pressure, and this is how we look at the performance. And this is the most important graph, and it is used to design a lot of activities. You can design your tubing size, you can design the triple safety valve, and so on using this graph. But this graph is not as simple as you see here. It's a very straight line, nicely made a straight line. And actually, it is not straight line because there are multiple factors. But in order to just uh, give you the concept, we are talking about the IPR. So let me repeat what is IPR. IPR is a graph is between and showing the relationship between the well flow rate versus the flowing pressure. For example, if you are producing 200 barrels per day, what will be the pressure? If you are producing 300 barrels per day, what will be the pressure? If you are producing 500 barrels per day, what will be the pressure? So this is what it is saying. And when you start producing max, there will be no pressure. Okay, there will be no pressure, and this is an ideal condition. Does not happen here when you talk about the absolute open flow potential.
Doctor?
Yes.
So the faster that oil comes out to the surface, the less the pressure in the pipes.
Yes.
But it doesn't make sense. Like if the pressure is high in the pipes, the flow rate on the surface should also be high, right?
Flow rate will be high. It means that's what you are saying. Flow rate will be high. The oil will come a lot. The pressure will decline.
Ah, okay.
Okay. If you put less pressure, less flow rate, the pressure will increase. This is the relationship. For example, this represents a particular well. Okay. For example, now imagine that here, for example, let's say this point. Now here maybe flow rate is, let's say, 200 barrels per day. So look at the pressure here. The pressure here could be, let's say, 2000 psi. But as, let's say, you're producing more, you are, let's say, producing now more. Let's say here it was 200. Here, and maybe here the pressure was, yeah, the pressure was 400, the flow rate was 400 barrels per day. Now, as you see that when the flow rate is increasing, the pressure is declining.
Sir, one question.
Yes.
When the pressure decreases, don't we use the enhancement recovery methods?
Yes. We use, yeah, we use the EOR methods or artificial weather when well stops producing at the surface. Okay. In this case, we are still producing 400 barrels. When it becomes zero, for example, at this point. Okay, this is the primary recovery. We are talking about initial stages of the well when there's a good pressure and we are producing it. After some point, 5 years, 10 years, there will be no pressure in the well and there will be zero production rate. The well will be off, shut, and oil will not reach to the surface. At that point, we do the enhanced oil recovery. Not at that point when we have some flow rate and we have some pressure.
Oh, yeah.
Yes. Yes, please go ahead.
Oh, no, I understood. Thank you.
Yeah. And any EOR methods we use when there's a no pressure and oil is not reaching to the surface. and then we do the enhanced oil recovery. Otherwise, according to this graph, we have flow rate, let's say 400 barrels per day, and at subsequent time we have the pressure inside the tubing. And as I said, we have to look at the well performance. What well performance we are looking at, how the pressure is behaving when we are producing at certain flow rate. Okay, this is particularly important when you have a moderate pressure. There are some wells in Kurdistan, for example, there the flowing bottom hole pressure is 4,000 psi. Now, when you have a 4,000 psi, you don't have to do anything. Just sit down, relax, enjoy, and enjoy the production coming out of the well. But when you have the wells like whose pressure is around 1,000 psi, 1,200 psi, it is quite low. Now, if you lose more, your well will stop. You are at a critical condition. Okay, critical condition. Either the well will die or you just survive it by some analysis and so on. So in that cases, the importance of this well performance and IPR comes more. Right now in Kurdistan, there are many wells whose pressure is above 4,000 psi. Very good pressure here in Kurdistan. So they don't need to do these kind of calculations a lot. They just, even in fact, in Kurdistan, there's no lot of engineering. They just drill the well, put the wall, open it, they get oil, and that's it. They dance. That's it. They sell it, they make money, and that's it.
Sir, I noticed the title says incompressible fluids. So for compressible, should the line be more horizontal?
For the compressible fluids, it should look like this one. It will be curved, and that's where the complication comes, because as I showed you in a video, here it is. This is for the two-phase one. This is the incompressible fluid when you have only single fluid, which is, let's say, oil. We consider oil here. But when you have the two-phase fluid, when it has a gas and like compressible fluid, in that case, the IPR looks like this one. It changes after the bubble point. And bubble point is the first, till the bubble point, as you see, it's a straight line. But after the bubble point, it changes. Okay.
Yes, thank you.
We are still here. So now when you look at the designing, and this, we have a software for that. Let me see if I have it right now or not. I already requested to get it. We are waiting. One of them is approved. Now I have software I can show you. Okay, in the next lecture, I will show you the software, this one. And we will work on, one of our project will be on software to develop this IPR for a real well. This is just an ideal condition. And I will then show you how to use this IPR for your benefits later on. So this IPR, you can take few values at the surface and make this one, this IPR. And first value, you can just shut in the well, completely close the choke and see how much is the pressure inside one. This condition, it will tell you the pressure at this point. For example, when your flow rate is 0, you shut the well completely, you get this point. And the other point you can get at any flow rate, let's say you selected 400 barrels per day, what will be the flowing pressure? So you take 2-3 points and you make this graph and you keep it in your lab. And also you use it for your calculations and so on and production engineering that I will show you in this one and next lecture and so on. Now, after this IPR, let's look at the behavior of the reservoir, how the reservoir is behaving. The Darcys Law, we all know that is the most famous one. You will see this in again and again at many places here. So it depends, the Darcys Law depends on the flow rate, area, permeability, change in pressure over time, and the viscosity. These all are the parameters which are affecting the Darcys Law and the fluid flow. And here, when we talk about the Darcys Law, we talk about it should have an conditions. I mean, when we use Darcys, apply Darcys Law, it should represents the real environment we are talking about. As you know, we are talking about the steady state flow. Incompressible fluids means oil. Homogeneous formation means there is no change inside the permeability and porosity throughout. And laminar flow we are talking about. But this linear flow model, which is the most easiest one, has no application in real way. But as introductory for fluid flow, we talk about Darcys law in linear direction, which comes from one side to another side. But in reality, in reservoir, We don't have a linear flow. We have the radial flow. Radial flow means oil can come from the side in a curvature style. So here linear flow means only in one direction, straight direction, that I showed you videos in the last one also. And so on. Now let's look at it, that what we are talking about in radial flow for incompressible fluids. For incompressible fluids, we have a different equation, and this is the for the linear flow. That's the equation for linear flow. Flow rate depends on the permeability area, pressure difference, viscosity, and the length of the reservoir. Now, when we talk about the radial flow for incompressible fluid, we have another equation. And what are the assumptions that are made to derive that equation? Because if the assumptions are not met, the equation will be invalid there. The reservoir is horizontal and at constant thicknesses. It means that the reservoir here we are talking about thickness is constant, doesn't change. In reality, this does not apply. In reality, reservoir can be, the thickness will be in reality reservoir maybe look like this one. So here thickness is different. Here the thickness of the is different. But here, if you look at it, here the thickness is different. From here to here is different. That's the situation. Now let's look at, but in the assumption that we are deriving here right now, we are saying that the reservoir is horizontal and it's constant thickness, as you see here. This is the first. And the porosity and permeability are also constant. This is also not true all the time. The porosity may change because the reservoirs normally they do not are for 1 feet, 2 feet, or 100 feet or 200 feet. They are maybe kilometers, 5 kilometers, 10 kilometers. They are big. So they might not have the constant permeability and porosity. They might be different. The third assumption says that the reservoir is circular of radius r. The reservoir is circular and it has only single phase. Well, it is also not true. Single phase means only oil maybe. How oil can flow? As if you look at the drive mechanisms, the oil can flow when it has water support or gas support or something. It should have a drive mechanism. So single phase, no, there are always two phase most of the time. Okay, then reservoir has a circular radius and well is located at the center. Okay, this is okay. Well can be located at the center. Viscosity is mu and so on. So based on these assumptions, they have made an equation, which is this one. Now this equation is not the same one that what you saw before. Okay, but in using this equation, they can find out the flow rates. Here is the flow rate QS, which is the outer boundary to the inside boundary. This is the 141 is the constant, and viscosity, formation volume factor, permeability, and the thickness H, which is the thickness of the reservoir in vertical direction. And this is the external radius and the Wellbore radius. There are two more things important here. One of them the steady state conditions, and one of them, the other one is the semi-steady state condition. First, let's look at the steady state condition. What does it say? In the steady state condition, it says that fluid flow occurs in the reservoir across the outer boundary at the drainage radius if the volumetric flow rate into the reservoir equals to the production rate. Now let's look at it, what it says. We have the reservoir, which looks like this one. The steady state conditions says that pressure does not change over time. Okay, pressure does not means that pressure at this point, this point, this point, this point, this point, this point, here, here, here. If you touch any point of the reservoir, here, here, it says that the pressure is the same throughout, it does not change. There is only one possibility. There is only one possibility that the pressure will not change at particular location. So It happens only when, okay, you have the well here and you are taking the oil out. You have the well here, and now you are taking the fluid out to the surface. Now the fluid that you are taking out at the surface, let's say you produce 1000 barrels per day. This 1000 barrels per day is supported by outside boundary. Maybe you can say a water. Okay, maybe you can say maybe there is a water here. So this 1000 barrels, the moment you take it out, this 1000 barrels will move, will jump in here through the water. So in a steady state condition, the outer boundary, there is a flow between the outer boundaries. So in steady state conditions, there is a flow at the outer boundary. Any production is replaced by flow from outer boundary. Okay, for example, whatever you are producing is supported by water or any fluid which is outside, and is from the outer boundary it is supporting it. Okay, now if I stop it here, let's look at the definition. Here it is. Fluid flow occurs into the reservoir across the boundary, as I showed you in the it is across the boundary, it is showing at the drainage radius. Now, when we talk about the pseudo-steady state, the pressure is the same in pseudo-steady state also. I clear this also. Now, in this condition, again the pressure is same. In all the points, its pressure remains the same. Pressure is same everywhere. But this time, there is no flow from the outer boundary. The fluid is not flowing from the outside in the pseudo. In this time, this fluid, whatever is inside, whatever fluid you have here, the fluid is expanding. When you are producing, the fluid is expanding. It could be because there is a gas which is coming out from the solution as the pressure declines. Could be the drive mechanism of solution gas when there is a gas, or could be a gas cap which is expanding. Okay, or could be a water which is here inside the boundary which is pushing it up. So in the pseudo-steady state conditions, pseudo-steady state, condition, there is no outer boundary flow. Okay, the pressure is maintained via the fluid expansion only. This is the pseudo-steady state condition. Any question?
Sir, does it stay completely the same, or does it like decrease a little bit,
Uh,
the pressure?
Pressure in the pseudo-steady state changes, but I mean linearly. I mean you can predict it like in a straight line.
Okay, thank you.
But is maintained by the pressure, the fluid expansion. This is what they have defined. Now let's go ahead further, and this is the equation for a steady state condition. Okay, to find out the pressure difference or in the steady state condition from the outer boundary to inside boundary, and then we have this is the equation from this is the outer boundary external pressure, which is the PE. It is showing here, and PW is the pressure here near the wellbore. Rest all are given: viscosity, formation. V is the formation volume factor, and so on. This is the equation. Now, for the two-phase flow, this is all incompressible. We are talking about the liquids only. Okay. Then, sorry, I have a call, so I'll be back in 1 minute. Yes. So then this is the semi-steady state condition. Flow occurs solely as the result of expansion of fluid remaining within the reservoir. So expansion of fluid is only happening in the solution gas drive when there is a, uh, the gas is coming out of solution out the below the bubble point. When the bubble point has achieved, and after that the gas is coming out, then the pseudo steady state can be achieved. So for each of the cases, the situation, the equations are different. This one now, for example, this is the semi-steady state. Now this pressure comes from the expansion of fluids. This one, so it's a different pressure than in the steady state. This external boundary here, this pressure is showing the external pressure at the outer boundary here at this point. But in the pseudo steady state, the pressure we are talking about here is the pressure caused by the expansion of fluid. So it's a different pressure we are talking about here. Now let's look at the question we have. An oil well in the middle of the large reservoir, which is actively supported by water, has an open hole tested and yields the following data. The formation volume factor, as you know, converting the reservoir volume to the surface volume. It has the viscosity and the wellbore radius thickness. Test the thickness of the reservoir is 50 feet from top and bottom. This is the flowing pressure, 3,800 psig. At flow rate, 3,000 stock tank barrel. So for example, when you are producing 3,000 barrels per day, this will be the flow rate of the well. So what they want right now, calculate the reservoir permeability. Okay, for permeability, again, this equation already we have it from pseudo steady state conditions. We just put all the values. The external boundary is 44,500, pressure is given. Original static reservoir pressure is 4,500 psi. The flowing pressure is 3,800. All the values are given. You find the permeability, which is 96.3 millidarcy. Permeability, and as you know, permeability is the important factor that we have to know how to estimate the oil that we can produce from the well. If we don't have the good permeability, the well will not flow. And 100 millidarcy is not really a very good permeability, but it is not as a bad permeability also. Good permeability somewhere above 200 millidarcy is a good permeability of the well. And 100 millidarcy probably is the normal one. Then we have the another term, which is the productivity index. Let's stop it here and we will continue from the next lecture. So far, do you have any question from the IPR? Okay. We will talk about the productivity index in the next lecture.
Doctor, I have a question, please.
Yes.
About the Excel sheet that you sent to us. The
Yes.
deadline for it is gonna be Thursday?
Yes.
Can you extend the time, please?
Okay.
For
by Saturday.
sorry?
By Saturday is fine.
Saturday? Yes,
Okay.
it works.
Okay.
Thank you so much, doctor.
Okay. Extend it to the Saturday. I will post it.
Okay, thank you so much.
Okay.
Doctor, I have a question about the exam.
Yes.
So the file that you sent us, will the exam be the same exact questions, or this is just an example?
Exact questions.
For 27th?
Yes.
Okay, so if it's, you said if it's not on campus, you're just gonna do the oral exam, right?
No, we are changing to the written exam, but in camera. So you have to write on, open the camera,
Yeah.
do exam in front of me, take the picture and send me.
Okay, so we just need to know the answers of those questions in the file.
Yes, exactly.
Okay, thank you.
Okay. It will not be a surprising exam. So you will focus and study directly what you need to study. You will not go here and there. That's why I posted the questions.
Thank you.
Okay. Any other question? So the deadline for Excel sheet is extended to this Saturday. I hope it is fine then. Now.
Doctor, just one more thing. I just want to remind you to upload the lecture from Sunday and the presentation.
I'm doing it.
Thank you, Doctor.
Okay. See you guys then in the next lecture.
Have a good day, Doctor.
Have a good day.